team. Thank you very much for your invitation and for letting me present this important subject via video. Sorry I cannot be there with you guys. To obtain a copy of this presentation, you can just email me and I will send you this video to you. So my story with compositional data analysis started in Florence during the 32 International Geological Congress. At the end of the Congress, the last day, I met a group of Spanish guys mostly. They were in a room called compositional data analysis. And I entered, it was very interesting. Then they invited me to their biannual conference. And when I was there, especially on a break, everybody's having a good time, talking, commenting about ALR, permutations, closed systems, etc. And I asked, guys, what about correlations? Silence. It was like if I have jailed pork in the National Assembly of Vegetarians. So they said to me, what about correlation? Correlation do not exist. They are an illusion. Say, who said that? They respond, well, that guy, Carl Pearson, who was the inventor of the correlation. And he was the first to point out that there is the problem of spurious or not real correlation when we deal with closed systems. Say, what, I have been doing this wrong all the time? I say, yes, you were doing all right, wrong all the time. You cannot use correlation analysis on closed data like chemical data. Closed data refers to data that is estimated on the basis of a percentage or part per millions or part per billions, which means every single geochemical data. If I was another person and I decide that yes, they were right, this will be the shortest presentation on Discovery 2018. But being a Cuban, I'm very stubborn and say, no, this cannot be possible. So I decide to test their theory. So to do this, I created a model of a copper mineralization in a porphyritic environment, a couple of faults, and the mineralization, of course, is related to the fault. The original paper can be downloaded from Wikipedia at the link below the screen. This is an example of the data. As you see, it has major elements and also trace elements. And the initial data responded to the following pre-established conditions. First of all, it was a closed system, meaning that the sum of all the values was 100%, or very close to 100%. There were no zero values or below the detection limits. We're keeping this very simple. There were not statistical outliers. And there were embedded positive correlations. For example, between copper and arsenic, nickel, cobalt, and other elements. It means that I first put the copper values and then I put the arsenic values. If the copper will go up, the arsenic will go up. And if the copper will go down, the arsenic will go down. So I would get a straight, direct correlation. There were also significant inverse or negative correlation, like between potassium and calcium, silicon and aluminum, etc. According to these embedded conditions, any correlation analysis must give us these two coefficients, which I call the range correlation coefficient. And it's a pity I cannot be there to explain in detail how we do this, but basically any element that is next to each other, for example, calcium is directly correlated to sodium, is directly correlated to copper. At the same time, calcium is inverse correlated to magnesium, or silica is inverse correlation to aluminum. So that's very simply. So the first case, or my case, as I call my statistic, I just took all the data together, major and trace elements, determine the distribution law, and use Excel to calculate the Pearson correlations. And the critical value of student was used to determine the significant correlations. So that is the table of the obtained correlation that we have. For example, you can see here that there is a negative correlation between silica and aluminum. At the same time, there is a positive correlation between aluminum and iron, etc. Okay, so those are the correlations. And when I created my correlation coefficients, I obtained these two coefficients. And if we pay attention, you can see that the original correlations that I input in the data are there. We have the negative correlation between the silica and the aluminum, and we have all these correlations. But also, we have a lot of new correlations that are not real. This is what I call the spurious correlation. One of the best examples is the correlation between silica and titanium. As you can see, there is absolutely no correlation there. So yes, we obtained the real correlation that we put there, but we also obtained a series of spurious correlations that mud the results. If we map the anomaly that with the RCC1, we see we get some coverage of the main ore body. This is the ore body. This is where we got our anomaly. If the chemical guy would come to the VP of exploration and say, well, we should drill here, 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 and here. Yes, in a couple of cases, they will hit the mineralization, but most probably they will be drilling in empty spaces. Besides, it doesn't have any sense of the continuation of this anomaly. And this was our best correlation. So I wasn't still very clear. Let's say, okay, I would treat separately the major oxide and the trace elements and see if I get a better result that way. And we almost got the same coefficient. We almost got the same result, a little better defined the anomaly when separated the trace element from the major oxides. So in conclusion, yes, it is true. When you process data that in the normal way, you will get a lot of spurious correlation. Even when you separate major and trace element, you get better result, but still you get a spurious correlation. So, okay, my statistics is not good enough. What about theirs? Because, I mean, I'm still very stubborn. So, there is a program called CoDaWork that can be downloaded for free from the internet, of course, and it allows you to get your original data and transform to one of the three algorithms that they use, ALR, CLR, or ILR. They are almost the same. ILR is a little bit better, but more complex. But here I'm going to show you the result of one of these elaborations, the CLR. And as you can see, once we transform the data, the zoom now is 0, not 100. That means that the closed data has been opened. Once I transform the data, then I go back. You can do the statistic using CoDa. It's a very interesting way of processing data, but if you're not ready to go there, once you transfer the data, you can go back and use Excel, CStat, whatever you're using to do the Pearson correlation, and that was the correlation that I obtained. And here is how it looks in the map. As you can see, we have a much better result. I mean, most of the anomaly is covering the copper project. Now, if I only use the strongest correlations, like above 0.95, I get these two coefficients, and the map is almost a perfect spot on top of the zone of mineralization. As I mentioned, they use two other ways of processing the data. One is called the ILR, it's the coefficient I obtained, that was the map, perfect. And the ILR, which is the best, I obtained also a very good result of the maps. You can go with any geochemist can go with that map and start drilling. As you can see, it's right on top on the center of the mineralization. So we get rid of the spurious correlation. We can process the whole data, measure and trace elements at the same time. There is no need for testing for statistical outliers or distribution laws. It's like you have normalized your data. And now you can believe in your geochemical maps, which is a very good thing. Now, wait a minute. What about factor analysis or principal component analysis? If we apply factor analysis for the raw data, we get the coefficient to the left. The IRL transform data, we get the coefficient to the right. And here are the maps. Yes, factor analysis is very good, but the only problem with factor analysis, you need to understand what each factor represents. And that requires a very good understanding of the geology, which not always you have. And in any case, the IRL transform factor analysis gave even a better result. So my final conclusion and recommendations. If you want to keep using the old way of processing your data, please only use strong correlation above 0.9 or 0.95. That way you will be sure to get only the real true correlations. And of course, factor analysis gives you a very good result when used together with your brain. But if you want to get all the information for your data and be sure that there are no spurious correlation, that you don't need to do testing for outliers or distribution loss. I mean, it makes the system the processing very fast. Well, welcome to the CoDa family. I thank you very much for your attention. I remember that the original paper can be consulted on Wikipedia right here. And I also want to mention a recent book that I published. It's called Exploring Geological Data with Weka, CoDaPack, and Inside. It's a step-by-step illustrated guide of how to use not only compositional data analysis to process your data, but also how to use artificial intelligence in elaborating your data. Again, thank you very much for the opportunity. Have a great day.